Okay, so welcome everyone. As always, or at least as last time, even worse than last time, technical problems, but we are on. So welcome to this reading group session on ODEs, so ordinary differential equations, and you can switch now. Thanks. So this is just the friendly intro, but I like starting my presentations with like looking up on Wikipedia, like whatever the day the presentation happened, any interesting events or people who were born or died. And it turns out that two important mathematicians were dead, and unfortunately not born, but died on February 18th. One was Sophus Lee, a Norwegian mathematician who worked a lot on these differential geometry and symmetries. So, like whenever you do any kind of differential geometry, at some point you hear about some stuff called Lie derivatives and stuff and so on. That from this guy, and it's basically a lot of ODEs and like continuous symmetries. So, it was like a major mathematician in the 19th century. Another one who died in 18th of February was Jacobi, who gave us the Jacobian among many things, and he was actually someone who did a lot of work on the theory of differential equations. So yeah, stuff to think about. Thanks. So the outline for today is really ODE 101 any percent. So I'm going to like blaze through the what I think are the most important like things to know about ODEs and how to solve them. And so literally we're going to start with what is an ODE, basic ODEs and how to solve them. And we're also going to specifically look at linear ODEs, so stuff when you have just like something like the derivative of x is equal to a to x, where a is some kind of matrix or this thing. So this kind of type of linearity, because these are super simple to solve. You can solve them explicitly, and they are useful all over the place. So we'll see about that. And then we'll conclude with like a brief, like the briefest of explanation of neural ODEs, and this will basically be the primer for the next sessions that will be delving deeper on these ideas. So next, please. Okay, so differential equation, simply put, it's a functional equation because the variable, the unknowns that we're trying to find are functions of some parameters, and it's a functional equation involving some derivatives. For example, the one here, so the derivative of x with respect to t is equal to 2 times cosine of t minus x of t. So that's a functional equation because we have a function x that depends on t, assuming t is just a real number here, and we'd like to find a function x that satisfies this equation. So if we find some x that satisfies this, it's called a solution, and there can be more than one. So we have to be careful. And so a solution is just a function or a differentiable function x that simply satisfies the equation. And in this particular case, we can find multiple ones. For example, if you try x of t is equal to cosine of t plus sine of t, and like you apply, like you compute 2 cosine of t minus x of t, and or the other one, you take the derivative of this expression, you'll end up with the same at the right-hand side of this equation. And similarly, if you add like a e to the minus t term, that's still a solution. And in fact, any if you add any terms like c, just a constant times e to the minus t, that's also a solution. So here we can see that we actually have like an infinite number of solutions. And so one thing that's important, at least in the theory of differential equations, is to ask, okay, when do we have a solution, so existence, and when do we have only one equation, an equation solution? That's uniqueness. I'm not going to talk about this because, yeah, for most reasonable systems, we know that there's only one, and usually people don't even bother checking. So, but an important thing is that if we have just the equation, indeed, we'll typically have infinitely many possible solutions. But which is why typically we're going to nail down one specific solution by using some kind of other equation or constraint on the function x that we trying to find. So like broadly, you can call them like boundary conditions. or initial conditions, for example. So here we just put that, ask that x evaluated at 0 is simply 0, but we could have like x of 0 being anything we want, or x of some any other number being anything we want. And usually that will nail down the yeah, only give us one possible solution for that. And so I think in English it's the when you have the ODE plus the initial condition, it's called an initial value problem, but you can have other types anyway. So yeah, next. Thanks. So a very, very quick zoo of like ODEs, because like ODEs are the bread and butter of science. Whenever you do physics or chemistry or any kind of serious work in those areas, you need to use differential equations, because most of the interesting properties of the like physics or the universe, you can't really find a good functional equation for them, like a good expression that gives you what you want, but you can describe it as an ODE. And so even though we cannot find like an explicit solution of the ODE, being able to model your problems and an ODE is a pretty good step, and usually the best you can do. But some like quick examples. So from the left, we have like the generic form of what's called a first order ODE. So one thing to keep in mind, we have like multiple derivatives involved. Like we can have the nth derivative of our function equals to something, and so on. And so whenever we have this equation, we're going to look at the highest derivative that appears, and that's going to call the order of the equation. So we have only one derivative, it's called the first order ODE. And yeah, I have a couple of examples on the bottom. So we have just dx of dt over dt is equal to some constant k times x. That's basically the simplest ODE you could think of. Maybe not quite the simplest, but almost the simplest. And it's called the solution to that is basically exponential growth or exponential decay. So it's actually a pretty important one. And if you had basically take the same equation and add a constant to it, you get something called Newton's law of cooling, where basically your system is going to like settle down at some temperature that's prescribed by the parameters of the system. If you like add another order to the equation, like take the last one here, we basically have like a second order term, a first order term, kx, and then some f of t. That's sort of a very, very generic form of what's called a dampened oscillator with driving force. So the oscillator basically comes from the second order. Like if you just have this second order term and then kx and the other thing equals 0, that's called a harmonic oscillator. And that's basically something that's going to oscillate back and forth between two values. And this dx over dt term, it's called a drag term or a dampening term, because it basically means you have like some resistance to speed. So basically, if you have this dx over dt term, you're no longer going to have like a perfect cycle, but you're going to like decay. You're still going to oscillate, but decay slowly towards 0. And then if you have an f of t term that's not 0, that's basically like a force like pushing down your system in some way. And notice that here it depends on t. Yeah, on the bottom you can see like some very common notations. Um, yeah, just something to keep in mind that typically we have a dot on the top, and that means just dx over dt, and a prime for d over dx. Like typically people would be writing these in a very terse way to like save space. Anyway, and also you can have like multiple variables, not just like time or whatever. And if you have like multiple derivatives, that's called a partial differential equation, which are typically a bit more involved and complicated, but they're still interesting. And so we have like a couple of the most common ones. The second one might be the most interesting, at least it's the one I like the most. It's called the heat equation. Um, it basically says that the time derivative of a function u is equal to the second derivative, spatial derivative of it. Um, and remember maybe from last time, the second spatial derivative is basically the curvature. And so that not only describes like how heat would like spread around some kind of piece of metal, but it's also called the diffusion equation, and is literally the same mechanism as diffusion in diffusion models. So like it's a very simple equation, but it has a lot of interesting properties. Okay, next. Okay, so let me have a drink. Now, one thing you might have to care about with your equation, so I mentioned you usually want to be sure that you have a solution and that it's unique. But sometimes you can have an equation that's going to blow up in finite time. So what that means is that you start your equation, but then after some finite time, it's like diverges to infinity. So the simple, very simple example is this one. So the x dot, so the time derivative of x is equal to x squared. The generic solution for this is simply 1 over c minus t, where c is some constants. And so you can see that basically whenever you do this, you're going to, in some finite time here, just a little bit over 1, you go to infinity and you stop. And so that's one thing to like people, at least in theory, care about this to make sure that I'm not going to like explode to infinity. And for example, so like some very important mathematical problems today are about this kind of questions. So you may have heard like the Millennium Prize for the Navier-Stokes equation, which are basically a very complex set of PDEs describing fluids. And the thing is that we still don't know whether these equations are like well defined and that they don't blow up. So if you can find like a proof that the Navier-Stokes equations don't blow up like this, you have $1 million, and maybe you can buy like however many GPUs that would be. Also, like this kind of phenomenon is literally called a singularity. So like whenever you see people talking about singularity, now you know better than them probably what it means. Okay, next please. Right, so I mentioned some very fundamental equations. So the first one on the left, we already sort of saw it. So it's y dot is equal to alpha y, where alpha is some uh, some real constant, but it could be complex if we feel like it. And the generic solution for this is simply going to be c, a constant that depends on your initial condition, times t to the alpha e to the alpha t. And so here, depending on the like sign of alpha, if alpha is real, if alpha is positive, then we have exponential growth. We go to infinity in exponentially fast. If alpha is negative, then we have exponential decay. And so instead we go to 0. And for example, this exponential decay is like the way people would describe radioactive decay. Like if you have a piece of radioactive material and you like measure the amount of like radioactive particle that you get out of it, that number is going to follow an exponential decay like this. The one on the right, so it's a second order ODE. It's basically y dot dot, so the second derivative of y with respect to time is equal to some constant and y. It's a special case of the ODE we saw previously. It's the general solution is basically going to be some combination of sine and cosine of kt. Again, all of these you can like compute them yourselves. This one basically is like you could think of it as like the fundamental equation that describes some kind of periodic motion. So both of these super important because they're simple enough and you can usually reduce your more complicated equations to something like this. But the one on the left is probably the most useful. Okay, next please. So at this point, at least if we're in a standard ODE course, basically we'd be going over like a lot of methods to manually solve ODEs. Like you have stuff like separable equations, all that jazz. We're not going to be talking about that because one, like these techniques have been literally handed down for generations. If you look at like the a modern ODE course today, chances are it's going to look quite a lot like the old ass ODE course from like the French mathematicians in the 1800s. So yeah, unless you're an engineer, this is not interesting to you. And it's especially non-interesting because almost interesting, at least non-linear ODE, um, usually you cannot solve them analytically. So you cannot find like an expression for the solution. So these techniques basically are not useful to you. And at least for most purposes, if you know the basic, like especially the linear ODEs, that's good enough for doing at least some qualitative analysis of your equations. So basically, that was it for the manual old-fashioned way. We can move to the next slide to solving all these numerically, which you might be more familiar with. So you can find a very simple scheme for like numerically computing the approximation of an ODE on a computer, and it basically just like adapts the finite difference formula. So basically, the finite difference formula is the one on the top here that tells you that if you have a like differentiable function f, then the derivative of f at some point t is simply approximately f of t plus h minus f of t divided by h for h as small enough step. And so if you just manipulate this a bit, that tells you that f of t plus h is approximately f of t plus h, your step size, times the derivative of t. So if you have a function that can compute f prime of t, then you can do this and like compute the solution to the ODE. And so the generic you might take like a small step size h larger than 0, and it gives you something called the Euler's method. And I have like yk plus 1 is equal to yk times plus h times f, which might depend on y of k and t of k. So one important, that's more details, but important to know about. So Euler's method, it's what's called a first order method. And that tells you basically how the error, so because this is an approximation scheme, you have an error between this and the true solution. Uh, I had planned like a nice interactive visualization of this, but since I cannot show you my screen, um, yeah, unfortunately no demo for today. But basically, this is an approximation, so you might need to tweak this h parameter to get a good approximation. And with all the methods, what you get is if you reduce h by some factor, let's say 2, okay, yeah, I forget like half, so reducing h by half reduces the error by half. So you get a linear return on like tweaking h. And this is very suboptimal. Euler's method is far from the best method. And typically when you want to solve complicated ODEs, you don't use Euler, you use a higher order scheme, like typically something like Wunschroter 4, which is like fourth order. So if you like divide h by 2, then your error descends by like 1 over 32. So usually a pretty good deal, but the thing is that this typically costs more in terms of functional evaluations. And so for like stuff like diffusion models and neural ODEs, depending on like the model you have, that might be too costly, but typically you want to use a higher order method. Okay, next please. So a small interruption before we go to the next part. So if you look at this first order ODE, so the x dot is equal to minus the gradient of f, where f is some differentiable function from Rn to R, and you apply the Euler's method to this, basically you just get gradient descent. So in some sense, you can think of gradient descent as like a discretized ODE, and so that tells you also what happens when you take like h to be very small. That tells you that you should convert to this ODE, and you can sort of do a similar interpretation of other optimizers, but only to some point because optimizers and ODE solvers try to solve very different problems. So that was the fun tidbit for today. Next, please. So on to linear ODEs. So we're talking about an ODE of the form x dot is equal to ax, where x here is just in Rn, so n-dimensional vector, and a is just some square matrix R in so n times n. And briefly, you can think of this like a system of n couple of linear ODEs, or just a single ODE that still works. And if you remember the like the fundamental equation in the one dimension that we saw earlier, we might expect something like, oh, just take the exponential of a times t and we're good, right? And this x of 0 is simply the constant for the initial condition. But one question, and we answer that later, is whether this like e to the exponential of a of t even makes sense, right? Because you're taking the exponential of a matrix, maybe not so clear what that means, but let's keep the suspense. So next, please. So before I tell you the solution, you might wonder, okay, that's for first order ODEs, but what they have like higher order derivatives. And basically, there's a nice trick that you can pull, which is if you have like, let's say this equation on the top with like nth orders and it's linear because they don't mix. Basically, you can like isolate this dn, so the nth derivative on the right here, express it as basically all the others, and that's one equation, and all the other you know that uh, like dn minus one, yeah, d, the time derivative of dn minus one x over dtn, that's just the nth derivative of x. So you can sort of like do this daisy chain and you turn a single equation of higher of nth order into first order ODE, but with n dimensions, with the change of variables on the bottom. So typically you can like isolate the highest order term and do this trick. And so usually whenever you have an ODE, you just have a first order ODE. At least you can bring it back to some first order ODE. So keep that in mind. Okay, so next. So enough suspense. So we asked, okay, what does matrix exponential mean? And the trick for this is that we can like use the Taylor series definition for the exponential function and apply it to matrices, right? Because we can take part of matrices, that's easy. And so we basically define the exponential of a matrix as this one. So the basically the Taylor series, but you swap in the x with a matrix. This works. It's like it is a perfectly well-defined matrix for any matrix A. But we can do even better. So if A can be diagonalized, so we can find like eigenvalues and eigenvectors such that I can express it as the A as V, my eigenvectors times lambda, a diagonal matrix of eigenvalues and V minus 1. Then the exponential, basically like you can find this just by expanding the powers of k here. You basically get to that the exponential of A is simply V times the exponential of your diagonal matrix lambda times V minus 1, and then the exponential of a diagonal matrix is super easy. You just exponentiate the terms on the diagonal. So super easy. Note that not every matrix can be diagonalized, so this doesn't always work, but for most nice cases it does. And so if we go to the next slide, what is nice about this last part is that we can just look at the eigenvalues of A, and that's going to tell us about the behaviors of our system. So if we have like some positive eigenvalues that we know that in this direction we're just going to have exponential decay, not decay, exponential growth. So we go to infinity. If we have negative eigenvalues, that's going to be a stable mode because in that direction it goes to zero. And then if we have like lambda equals to zero, that's basically something that stays constant. You don't really move along that direction. And if you have like complex eigenvalues, the these the imaginary part basically tells you that you are going to have some oscillations. So you have, like, if you remember e to the I theta, right? That's a sine of theta plus cosine I cosine of theta, or maybe the other way around. Yeah, cosine theta plus I sine theta. So basically, you get something like these oscillations, and then if you mix these, you get like decaying or growing oscillations. So, and if you have a mix of those two, you can like have some funny business, but that might be fun at the time. Okay, next, cool. So on to neural ODEs. So I told you like this is really the speedrun any percent. So we're going super fast. Um, like I just love how if you just look at the neural ODE paper, basically they just they say it's all in the first paragraph because they noticed that people started using residual connections because it made the model train better. And it looks like basically you're adding the input to your layer output. So you have h of t plus 1, h would be like the hidden activation, and you add the previous one, so h of t plus f of h of t, and f is like your essentially your one linear layer. And if you squint just a little bit, this is basically just Euler's method again. Um, right? Because we could imagine there's like a scaling parameter or a step size in front of this little f, and that would basically be Euler's method. And so their brilliant idea was, okay, let's just have a layer, a neural network layer as an ODE. So have stuff like h prime of t is equal f of h of t times theta and t, where here f can be just a neural network with some parameters theta. And okay, so far so good, but what makes this work, if you go to the next slide, thanks, is that first of all, you can compute the backprop through this efficiently. So you don't have to like use backprop through every single operation of your ODE solver. That would be very painful and basically you'd run out of memory. Uh, you can use something called the adjoint method, which is like a classic ODE stuff, to directly compute the what would be the adjoint, so your backprop through your ODE solve. And so that's nice because it just gives you to compute the backprop, you only need just another to solve another ODE. It's nice because one, you can treat the ODE solver as a black box. You don't really need to care about whether you're using Euler or something else. You can choose. Another nice thing is that this kind of model can natively handle irregularly sampled data because now time is a continuous parameter. So if you have data like a time series model with time at like random times, that's would be usually a pain to do with something like an RNN. Here, no problem. You just apply just ask your ODE solver to stop at these times, and you can compute the loss without any problems. Another thing is that, so I mentioned like basically basic Euler solvers, but typically what ODE solvers are a bit smarter because they adapt the step size. So they look at the like the computed estimation of the error, and based on that they can decide, oh, this here I can take a larger step, here I have to make a smaller step. So these are called adaptive solvers because the step size adapts as you go along. And so that's nice because it means you can interpret this like this ODE as like an infinite depth neural network, which might be a bit overblown or exaggerated. It's maybe more accurate to say adaptive depth because like the amount of computation that you're doing depends on your input and it's like nicely dependent. So yeah, that's the like the main arguments that they pose for neural ODEs in their paper. But of course, now we know that there's like a lot of applications. Like you have diffusion models, which is some cases of diffusion models that use ODE solvers. And then the big one, which at least for me is interesting, is basically scientific machine learning and pins, where the idea is that you have like a physical model, like let's say you have like the equation of you're trying to model COVID, like the spread of COVID for a population, and you know some terms, but some piece of the model you don't exactly know. And the brilliant, the galaxy brain idea here is just to take the parts you don't know, and just stick a neural network in there and ask it to learn the right thing. And it's nice because you can still build in some constraints about what kind of function your neural network should learn. So like these models are super nice, at least for science people. Okay, that was the end of the speed run. So where do we go from here? We have a lot of options. So the next obvious step would be state space models because they're all the hotness right now. And like what we've just seen, we've basically done like almost all of the background for that. So like it would be super easy to go there. But there's other like weird and evil stuff. So for example, I don't know if you guys have had heard of like reservoir computing of liquid state networks. Um, like they're basically like a very simplified kind of neural ODEs, at least for RCs. But like reservoir computers in particular is something that like I don't hate, but it's shocking to me how they can work. Like even more bullshit than whatever most bullshit thing you saw in machine learning. Reservoir computing are offensive in how they somehow manage to work. Um, but then there's other stuff like basic chaos theory or dynamical systems. If you saw the like this blog post about fractals by Yasha Soldikstein, um, that's basically chaos theory. He looks at the behavior of like training neural networks as a dynamic system, and lo and behold, you find some fractals, and if you see fractals, that means you have some nasty stuff going on. That basically means you have chaos at some point. And then, of course, anything else people might want to go there. Okay, so I see one, the usual person actually asking questions, so go on. So the blog post by Yasha Soldikstein, I'm sure someone is going to link it here soon. Uh, I have faith in the people who are off topic. But yeah, like, if you guys want to talk about chaos theory, that I'd be super down to do that. So, but it would take like an entire session to explain. As I understand them, LSMs and reservoir computing are basically just spiking neural networks, which themselves are basically just small recurrence instance. Uh, yes and no, at least maybe for liquid state networks. Um, but if you look at like how people construct these reservoir computers, it looks like utter bullshit. Like you look at it and like, no, it is fucking works, and somehow it does. But I might be not up to date. At least I'm definitely not up to date on liquid state networks. You have issues with what I said back on slide 14. What did I say that was wrong? Go on. I can think of maybe many things. I bounded the final statement in the complex plane non-inclusively. Yeah, I mean, I was severely hand-waving this part. The thing is that if the way I had planned to do this is to have like interactive illustration showing basically what happens. I sadly cannot do that, but maybe I'll post the code for that. But yeah, I'm still not sure exactly what you meant. Yeah, I agree that I might have phrased that not so great, but yeah, I mean this part, if people are a bit confused about, definitely go read either DiffyQs or one of the other sources. Like I think they all show like analysis of this, but for two-dimensional systems, and that usually tells us a lot of interesting stuff. But yeah, indeed, I was severely hand waving this what I said in this part, so be cautious. Okay. Okay. So anyone else has questions or request for what we should cover next? Chaos. Nice. Nice. I'm actually super glad that people want to hear about chaos because it means they can open your eyes to how cursed it is. Neural PDE solvers, yeah. I mean, if you want to cover neural PDE solvers, go right ahead. It doesn't always be me presenting. But yeah, if people, I mean, I think probably we're going to do still state-based models for next because that's going to be like a quickie, and then we move on to chaos, and I show you how deep that rabbit hole goes. So how deep are we talking about chaos theory? So if at least the way I'd cover it is mostly explain what chaos is. Like let's give the obviously the definition, but again defining exactly what chaos is a bit complicated. But basically understanding what exactly that chaos is, that's a major like it's really weird and it should be shocking if you understand it correctly. So my goal would be to like make sure that you guys are shocked that this kind of demon can exist. I don't know if that answered the question at all, but neural PD solvers for chaotic flow. Yeah, of course. I mean, probably you should do neural PDE solvers after state space models in chaos. That sounds like the easiest. Okay, so yeah, so consensus at least. Yeah, I'm noting that people want to learn about chaos, which I'm very happy about. Um, yeah, we'll do that after state space models because that's really easy, and then we'll keep going. Is there another last question? Signature transforms. I'm not familiar with it, so if you can link it in the thread, that'd be cool. Um, I think I will still have to do something about reservoir computing because yeah, it does disturb me how bullshit it is. But okay, so yeah, we have a lot of interest, so it's cool. So thanks everyone for coming here and for asking all these questions. Thanks Hawk for doing the last minute slide displaying. That was awesome. Hopefully, I can like exercise whatever decided my computer to be fucky about this. But anyway, thanks everyone, and see you guys next time.